Okay, we will continue. So today we won't start anything new. I'll finish this Gaussian elimination module, and then we will. If you guys have any doubts so far, because everything till today will be in the midterm on Thursday. And one more thing, I'm not again available tomorrow, so we'll have to shift tomorrow's class to either preferably Friday. Yeah. So that means the next class is your midterm. It'll be for, let's say, half an hour to 45 minutes, uh, and everything that we covered till today. Okay. If there are any questions so far, we can discuss after I finish uh, the Gaussian elimination module. Okay. So last class, we saw how to solve a general system of linear equations and get it to, and once we get it to the reduced row echelon form, then we can essentially find out if it's solvable. If it's solvable, we can find out the unique solution if it exists, or if there are infinitely many solutions, then we can find a general expression for uh, the complete solution like this when it's solvable. And one of the major themes in linear algebra is the idea of so matrices play an important role. And one way to understand what a matrix does or its properties is, of course, knowing the four fundamental subspaces. In addition to that, it turns out writing a matrix A in terms of other simpler matrices which have specific structures tells us something about the matrix itself. Okay, and these are usually called matrix factorization methods. Where you are factorizing a matrix into simpler matrices, like you factorize a number into prime numbers, right? The same idea exists here. So we would expect express like this as a product of two or more matrices, and the matrices B and C have some simple structure or have some special structure that reveals what A is actually doing or what is the structure of A itself. Okay, and we'll see several of these matrix factorizations throughout this course. And the first one we will look at is called the LU factorization, okay, which essentially comes from Gaussian elimination. And matrix factorization will apply, so specific matrix factorization methods will apply for only specific matrices, the matrices that satisfy a particular criteria. And they don't apply for other matrices. But there are other ones like the SPD, which we will see exist for all matrices. Whatever matrix you can think of, you can always do a SPD factorization. Whereas LU, you cannot do for any matrix. There are only specific matrices for which you can do this. Right? So in the LU factorization, we essentially want to be able to express a matrix A as a product of two matrices, L and U. And the reason for the choice of the alphabets L and U is L is a lower triangular matrix and U is an upper triangular matrix. And we can do this whenever your A is a square full rank matrix. Okay? We can express it as a product of a lower triangular matrix followed by an upper triangular matrix. Okay? There is one more condition where for this to apply, but that we'll see that a couple of slides later. Okay, and the way you do this is essentially the way you obtain the LU decomposition is by following the Gaussian elimination rules for a square matrix. Okay, and for now we will assume that when you do Gaussian elimination, it does not require any row exchange operations. Okay? If your matrix A, when doing Gaussian elimination, requires row exchanges, then it turns out you cannot write it like this: A equals LU. You have to do a slight modification. Okay. So before that, what are the three Gaussian elimination steps? Yeah, there are three steps now. What are the three steps? Sorry? Interchange. Okay. Interchange what? Interchange what? What is EI? Are you sure? It has to be the other way around. Okay. Interchange rows. Okay. Where's the other one? Sorry. No, no. What are the Gaussian elimination steps? That's what you're trying to get eventually by doing those 3 steps repeatedly. Sorry. Replace what? Yeah. That means you scale. No, no. You're not replacing EJ by alpha EJ. You said, is it, or EI? That's okay. That essentially means you're scaling. What is the last one? Well, add a scaled version of another row. Okay. Here, EJ becomes EI, EI becomes EJ. Here, EJ becomes alpha times EJ. Here, EJ becomes EJ plus alpha times E. Okay. You're doing row operations. Let's say I have this matrix A, and I want to get a new matrix such that the first row is alpha times the first row of A, and every other row remains the same. Okay? I want to get this A cap. The only difference between A and A cap is all the rows are the same, except for the first row is alpha times the first row. First row of A cap is alpha times the first row of A. Can I represent this transformation from A to A cap by doing a matrix multiplication operation? If yes, then you have to tell me what would be the matrix, and would you have to post multiply A by that matrix or pre-multiply A by that matrix? Essentially, you have to go back to, when you say A equals BC, you have to go back to what matrix multiplication does. What can we say about the rows of A in terms of B and C, matrices B and C? Same rows as B, right? Is it? If it's same rows as B, then A will be equal to B, right? Rows of B are equal to rows of A. That means it's the same matrix. So that's not correct, but it's correct. So that's not correct. That's yeah. Okay. So we saw that when we do matrix multiplication, the rows of A are the linear combination of rows of C, and the exact mixture for the linear combination comes from B, right? That means if I want to just modify the rows of A, I should be pre-multiplying it by some matrix. Okay, I'm going to call it E. Okay? Now we need to figure out what is this matrix E, and what we want is the rows of A and A cap are the same, except the first row of A cap is alpha times the first row of A. In that case, what would the matrix E be? Let's take this example: 1, 2, minus 1, 4. I want to find a matrix E such that what I get here is 4, 8, minus 1, 4. Now tell me what will be this matrix E. What will be the shape of the E matrix? 2 cross 2. That we know. What will be the elements of E? 4. Okay. Here, before telling it to me, no, you can simply write it down. Whatever you think and multiply. That's why I gave you 2 cross 2 example so that you can write it down, so that it's not abstract. 4, what will be this? Zero, is it? Okay. Here, you don't have to struggle so much. The first row is a linear combination of rows of first row here is a linear combination of rows of A. How much of each row you're going to take comes from the first row of E. So here, the first row of A cap is simply 4 times the first row of A. That means you're only taking the first row and multiplying it by 4. So you take 4, 0. You take 4 times the first column, 0 times the second column. The second row, sorry, 4 times the first row, 0 times the second row of A to get the first row of A cap. Starting from the second row, all the rows remain the same. That means you only take the corresponding row. Everything else is 0 except for the corresponding row. Here we are only talking about a 2 cross 2 matrix. So this is 1. So in that case, what would be the matrix E then? If this was an n cross n matrix, the first row of A cap was alpha times the first row of A, and all other rows remain the same. So then what would be the E matrix? If you can generalize from here. Yeah. Alpha here. The first row of A cap is alpha times the first row of A. That means I only take alpha times the first row. I don't take anything else. Starting from the second row, everything else remains the same. That means for the second row, I only take the second row, make everything else 0. And I do the same thing for all of them. And then in the last row, I take the last row only and not take anything else. If you do this, what you will have, if A was equal to A1 tilde transpose, A2 tilde transpose, so on, AN tilde transpose, then this will imply that A cap will be alpha times A1 tilde transpose, and then everything else will remain the same. Similarly, if I wanted the ith row of A cap to be alpha times the ith row of A, how would this change? Well, what if I wanted the second row of A cap to be alpha times the second row of A? Then how would this change? Yeah, this will be 1, this will be alpha. If it's the ith row, then the ith diagonal element will be 1, alpha, and everything else will be 1. That's all. Right? So that means the first Gaussian elimination step, or not the first one, the second one that you mentioned here, we can represent that as a matrix multiplication operation. Okay? And this is called an elementary matrix. One of the elementary matrices uh, associated with Gaussian elimination. Okay. Okay. What about the row exchange operation? Here, what if I wanted to exchange rows 2 and 1? What would be E? Okay, write the entire matrix down and multiply and see if that is correct. Hey, what approach are you taking? Are you saying, okay, I'm going to write this as A, B, C, D. I'm going to multiply this whole thing out, and then I'm going to solve for A, B, and C. Yeah, that's the high schooler's approach. It's too low level. Okay? The reason we looked at the four different views for matrix multiplication is because you need to now think a little higher level. Okay? If you keep doing this, you'll never get the other view. Okay? Here, we know you can still write it like this. It's okay to write it like this. I know the first row here will be a linear combination of these two rows, and the amount of first row I take and the amount of second row I take is given by A and B. So here, the first row of this A cap is simply the second row of A. That means I take 0 times the first row, 1 times the second row, I get this. Okay. Similarly, for the second row, is essentially just the first row of A cap. So second row here is the first row of A cap. Sorry, second row of A cap is the first row of A. That means I take 1 times the first row and 0 times the second row. That's it. 0, 1, 1, 0. Yeah. Yeah. So the second elementary matrix, at least in this case, will be 0, 1, 1, 0. What if I had a n cross n matrix and I wanted to swap the first row and the nth row? Okay, let's do a 3 by 3. Maybe that's also, maybe it's still a bit abstract. I'm going to call this row 1, row 2, row 3. What I want is row 3, row 2, row 1. Let's go row by row. The first row of, I'm going to call this A cap. This is A. Of A cap is determined by the rows of A, and the exact linear combination comes from the first row of E. Now tell me what will be the elements of the first row based on this. Yes. So, okay. Now, see, once you see that, then it's fairly straightforward. I want 1, 2. Yeah. Now tell me what it is. Yeah, it'll be 0, 0, 1. That's all. Okay. Now tell me if I need to replace, if I want to exchange rows I and j for a general n cross n matrix, what would this matrix look like? Well, I'm replacing rows, replacing the ith row by the jth row, or interchanging rows I and j. Well, in general, we don't know what are I and j. I and j could be anything, right? Only thing we can say is all rows except I and j will have 1 in their diagonal element. Okay? The ith row will have a 0 in the diagonal element and a 1 in the jth column. And similarly, the jth row will have a 1 in the ith column and 0 everywhere else. Okay? That's your second elementary matrix or elementary matrix for this. Okay? So that's the secondary elementary matrix. Now, let's look at the third operation. Once you're able to see it like this, then things become a lot more easier. This is the third operation where you want to add a scaled version of another row to the current row. Okay, let's say I want to keep R1 as it is. I want to add alpha times R1 to row 2 and keep row 3 the same. Now tell me what will be this E matrix. That's all. Once you get this, then what if I wanted to do this? Yeah, that's all. That's essentially your third elementary matrix. Okay. Now, whenever you do the Gaussian elimination steps, right, you're simply taking A. Let's say you're doing step 1, you're multiplying it by some elementary matrix E1 to create a 0. And then you do another step to create another 0, another step, so on and so forth. Let's say you keep doing these steps until you get an upper triangular matrix. Okay? You simply multiply all of these together. And then if you get a matrix E, this will be a composition of all the elementary operations that you did or the Gaussian elimination steps that you did. So these are the three matrices corresponding to uh, uh, the three steps that we do in Gaussian elimination. I'm giving a 4x4 example here. Okay. Well, you already see, I've already written the text here, but this essentially means row 1 remains the same, row 3 remains the same. You're exchanging row 2 by row 4 and row 4 by row 2. Here, all the rows remain the same, except you're scaling the second row by alpha. And here, row 1 and 2 and 3 and 4 remain the same. Here, you're adding alpha times row 2 to row 3. With those steps now, let's now do Gaussian elimination for this matrix. Okay? But we will keep track of the corresponding elementary matrix for each step that we do. Okay. Okay. We have 1, -1, 2, 2, 0, 2, 4, 2, 1. Okay. The first pivot is non-zero. So we don't have to do a row exchange operation. The next thing we try and do is make this 0. Right? Okay. What elementary operation would you have to do to make that 0? I'm going to write those matrices here. I'm going to start from the first matrix here. What is the first operation that you do? R2 minus 2 R2. What will the corresponding elementary row operation matrix be? No, what will be the first row? Okay. When you do that, what matrix do you get? When you do E2 is replaced by E2 minus 2 E1. Or row 2 is replaced by row 2 minus 2 row 1. So row 1 remains the same. This will be 0. Guys, maybe do it. Do it and tell me. Minus 2, okay. And for now, we'll keep this unchanged. What is the corresponding elementary matrix now? So that if I multiply this matrix here, I will get this. If I pre-multiply this matrix by this matrix, I'll get this matrix. Okay. Did you do anything to row 1? No. Did you do anything to row 1? No, you did not. Then this is fine. Did you do anything to row 2? Yes, what did you do? Minus 2 times. Minus 2 times what? So what will be the corresponding row? minus 2, 1, 0. What about the third row? That's all. That's the first elementary matrix. And from this, what do you do? Row 3 minus 4 times row 1 is new row 3. So row 1 and 2 remain the same. This will be 0. What will be this? Okay. It's probably correct. Okay. Now, what is the second elementary matrix? Okay. Hold on, hold on. No, no. Here, I'm going to call this E1. You multiplied this by E1 to get here. Now we need to multiply this by E2 to get here. That means this is already done. You are now operating on this matrix. Yes. What is it? Minus 4. So that's your second elementary operation. Now we go to the second pivot is non-zero. So no row exchange operation is required. Now we go ahead and then do what? So first row remains the same. Second row remains the same. Third row, we're going to do something. What is the third row? What is the operation that we're doing on the third row now? Starting from this matrix. Yeah. Yes. R3 minus 3 R2. That's it. So that'll give me 0. What will be here? What will I get here? Okay. All right. What is the corresponding operation here? Yeah. Yeah. Huh? Right. Once we get to here, we are done. Gaussian elimination is done. We've got an upper triangular matrix. Okay. Yeah. That means if this was A cap, right? Sorry, this was, if we started with A, I'm going to call this E2, E3. This would give me, I'm going to call this U. Okay. So if I take my matrix A and pre-multiply by these 3 Gaussian elimination steps, that means the 3 elementary matrices corresponding to the 3 Gaussian elimination steps that we've done, we will get an upper triangular matrix. Okay. Now, if you remember your matrix inverses, okay, what can you say about this? If I have a matrix A and B, both are square and both are invertible. Okay. What can you say about this? Will it be A inverse B inverse or B inverse A inverse? Okay. A simple way to remember is this. Okay. A and B are both invertible, right? That means if I want to eliminate A, right, from this, right, I multiply by A inverse. I cannot insert the matrix A in the middle, okay, because the matrix that I have is already is the multiplication of A and B, so I cannot separate them. I don't have let's say A and B separately. If I do this, I will get, so these two will give me I. I'll get B, right? And if I do this whole thing, if I multiply by B inverse, right, I'll get B inverse. That means the inverse for AB is B inverse, sorry, is A inverse, B inverse. This is if you come from the left hand side. You can check it for the right hand side as well. If I have AB, first I need to nullify the effect of B. So I multiply by B inverse. That will remove the effect of B. And then if I multiply the whole thing by A inverse, that will remove the effect of A and B. I'll get I. Okay? That means if I have a matrix AB which is invertible, B inverse A inverse is the inverse of that matrix, because if I multiply AB either post by B inverse A inverse or pre multiply AB by B inverse A inverse, I get I. That means B inverse A inverse must be the inverse of AB. AB inverse should be B inverse A inverse. Okay. Right. You can verify this statement later. All the elementary matrices are invertible. Okay. E3 is invertible, E4, E2, E2, all of them are invertible. Okay. If they are invertible, right, and if I, to this left hand side, if I multiply E3 inverse followed by E2 inverse followed by E1 inverse, this whole thing will disappear, leaving just A, right? I have to do the same thing on the left hand side. So before U, I will incorporate E1 inverse, E2 inverse, E3 inverse. Okay? That means I'll get A equals okay. It turns out, you can verify this later, the inverse of a lower triangular matrix will be lower triangular, and I think this was in the assignment, that the product of upper triangular matrices are upper triangular and the product of lower triangular matrices are lower triangular. Since each of these is a lower triangular matrix, the product of these will result in a lower triangular matrix, and that will essentially be our. Okay. So the way to interpret this is like this. U contains the end result of Gaussian elimination. Okay. And L is the matrix that will essentially undo Gaussian elimination so that you get A. Okay? So you did some operations to the rows of A to get U. If you want to undo those operations and get A back, that's the matrix L. Okay? And in fact, that's what these inverses mean, right? E1 inverse simply says I'm undoing the E1 operation. What is the E1 operation? E1 operation is add minus 2 times row 1 to row 2. What would be the inverse of that operation? How would I undo E1, this first step? Well, what have I done in E1? I've added minus 2 times first row to the second row. How do I undo it? Yes, you're right. What is it? No. That's what I mean. Undoing is inverse operation, right? What do you exactly do? What exact algebraic operation do you have to do? I've added minus 2 times row 1 to row 2. How do I undo that operation? Well, you add 2 times the first row back to E2, then your first operation is uh, removed. Okay. In that case, what is the inverse of E1 here? If E1 is this operation, what is E1 inverse? No. See, think about the operation in your mind in words, and then let's find the corresponding matrix. E1 is you add minus 2 times second row to the first row to the second row. Now to undo it, you have to add 2 times the first row to the second row. So what would the corresponding matrix be? Yeah. Yeah, that's it. That's the inverse. Okay. What about E2 inverse? In E2, you're adding minus 4 times the first row to the third row. What about E3? You added minus 3 times the second row to the third row. Sorry? Plus 3. So it'll be 1. Okay. Now multiply these 3 matrices and tell me what is the product. And that will be our L matrix. What is this product? E1 inverse multiplied by E2 inverse multiplied by E3 inverse. Then we have our complete LU decomposition. So we know U is 1 minus 1, 2, 0, 2, minus 2, 0, 0, minus 1. Tell me what will be. The first row of E1 inverse, E2 inverse, E3 inverse is easy to know. It'll be what? In fact, if you look at all of them, no, they're not doing anything to the first row. It's 1, 0, 0, 1, 0, 0, 1, 0, 0. So the first row of the product will be 1, 0, 0. Again, if you're doing computing each element, you're doing it the wrong way. Here, what do we have to do? Don't do it element wise. Don't do the inner product view. You should do the row view. One zero 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 one zero 031, right? This is what we need to multiply. Let's take the first here. The first row of this, the product of these two is, take the first row of this matrix and don't take anything else. So 1 times the first row, 0 times the second row, third row. So this will be 1, 0, 0. That's the first row. Second row is 2 times the first row plus 1 times the second row. 2 times the first row is 2, 0, 0. 1 times the second row is 0, 1, 0. If you add those two, you get. Okay. And you're not doing anything to the last row. So the last row will be. In fact, if you want to test yourself, you can do the column view as well. The columns of this matrix will be the linear combination of columns of this, and the exact linear combination is given by these. That means the first column here will be 1 times the first column, 4 times the second column. 1 times the first column is this. If you add with this 2, get 1, 2. 4 times the third column is 0, 0, 4, get 4. Okay. Maybe that is a little too fast now, but again, I would encourage you to go look at it that way. Don't do individual multiplication. That's the wrong way to go about it. That'll take forever. And you don't get understanding of what is going on. Okay. Now you tell me what will be the final matrix using the row view. What will be the first row? Sorry? The same as what? Okay. Same as what? There are two matrices, right? What are you really doing here? Explain this in words and then maybe then we can easily write down. Sorry. Yes, but what exactly are you doing here? You're taking 4 times the first row, adding it to adding it to the third row. 4 times the first row is 400. The third row is 031. If you add those two, 4 will come here. So 431. Okay, all right. I hope that's clear. So the product of these three essentially results in this matrix 1, 0. And as I said earlier, lower triangular, upper triangle. And as I said before, we can do A equals LU. We can factorize, we can do the LU factorization of a matrix A only if it's square and it's full rank. That means none of the pivots are 0. Okay, and there are no row exchange operations. In this particular example that we saw, we did not have to do any row exchange operations because the pivots that we looked at were all non-zero. And once we have the LU decomposition, right, it turns out you can solve X equal B fairly easily. Okay. The way you do that, you actually don't have to do any inverse operation. When we did Gaussian elimination, solving for X was easy because once you get it to the upper triangular form, what did we do to solve for X? What is the operation we did? We gave it a specific name. Back substitution, right? You find the last value and then go to the previous equation and keep substituting. Once you have the LU decomposition, it turns out you can very quickly solve Ax equals B by just doing two things, what is called a forward substitution and then a back substitution. And the way you do that is this. So if you have A equals LU and you're trying to solve Ax equals B. So we know A is LU, so let's replace it like this. Now it looks like you have to move L to this side, take the inverse, and then you will get Ux equal to some L inverse B. Then you can do back substitution. Because if you have upper triangular, then you can do back substitution. But we should not do that. We shouldn't try to take the inverse of L. What you can do is, let's say, this, a matrix post multiplied by a column vector will be a column vector. Okay. Let's say we'll call that Y. This is unknown. We don't know what that is, right? Okay. We first solve this equation. Okay. In this equation, because it's upper triangular, so it's like this: 1, 0, 2, 1. I'm giving you an example. Right? This is the first equation. Right? First equation only has y1, the component of y. So there you know what the value is y1 is. Then you substitute y1 in the second equation, and then you can get the value of y2. So you are doing forward substitution. So you can solve this by forward substitution. Once you solve for this, we know ux is equal to y because that's what we've assumed it to be. Here you can solve for x now by back substitution. So again, we don't do any inverse. You do forward substitution and back substitution. Once you have the LU decomposition. And again, once you have LU, right, then you can essentially solve any Ax equals B. For any given B, you can quickly solve X equals B. You don't have to do any Gaussian elimination or anything like that because you've already done that. That information is there in LU. Okay? Whenever you get a new BI, you first do the forward substitution to solve for Y, and then you substitute for Y here, do back substitution and solve for X. And the very nice thing about the Gaussian elimination step operation or the LU decomposition is, if you notice, right, the diagonal elements of your L matrix will all be 1. Okay. And it turns out that when you do LUD, let's say I have a, I don't know, huge matrix. Okay. That means I already need a lot of space to save this matrix in memory. But when you do the LU decomposition, it looks like, well, you've essentially now converted this problem of saving one matrix into saving two matrices, right? Because you have to save L, you have to save U. But it turns out you actually don't need extra space at all, right? You save U, and for the L matrix, we know the diagonals are all 1. That means the only thing we have to save are these elements. And these elements would essentially fit here. In the U matrix, where the lower, everything below the main diagonal are 0. So you can fit 2, 4, 3 here. So essentially, when you do LU decomposition, you actually don't require extra space to store L and U. It will require as much space as your original matrix only. Okay? That's a nice property of LU decomposition. Okay. The last thing we'll see is when LU decomposition does not, we don't have LU decomposition, even though A is full rank and square. Okay. I want you to do this by yourself. Find the LU decomposition of this matrix. Okay. So do the Gaussian elimination steps, and then find the corresponding E1, E2, E3 matrices, find their inverses, and multiply them together and get U and L. And you can tell me what the individual matrices are once you have them. So you have 1, 1, 0, 2, 2, 1, 3, 4, 1. Then you can tell me what is E1. Yeah. What is E1? Yeah. You're always missing the negative sign. You're subtracting 2 times the first one. Yes. Last one? Yes. That's fine. Okay. And what do you get here? Okay. And our pivot was this. Okay. What is the next step? Huh? Sorry. Okay. Yeah. You're telling me the elementary matrix. That's fine. 1, 1, 0, 0, 0, 1, 0. Zero, is it? 1. Yes. Okay. What is the second elementary matrix? 1, 0, 0. No, no, no. You're only operating on the third row. Yes, yeah. Okay. Same thing. Okay. Now, where is the pivot? The problem is you have a zero pivot. What do you do next then? Well, you do row exchange. So 1, 1, 0, 0, 1, 1, 0, 0, 1. And once you do that, you're done. Okay. But what is what is E3 now? We are done because this is upper triangular. What is E3? Yes. Are you sure or are you guessing? 1. Okay. That's all. Okay. Now this is so times A gives me U. I've already got my U. This is my U matrix. Now I simply have to move E3, E2, E2, E1 to the inverses to the other side, and then I'll get my LU decomposition. Okay. That means I have to now do E1 inverse, E2 inverse, E3 inverse into U, and I should then get LU. Now let's first write down what is E1 inverse. The matrix that undoes operation E1. Okay. What about E2 inverse? What about E3 inverse? Hey, hold on. That's the identity matrix. That means if I multiply E3 inverse by E3, right, I'll get E3. I don't get I. So that's not the inverse. Again, think in terms of words. What is the inverse? You did a row exchange operation. What is the inverse of that operation? Yes. You do the interchange. That means you do the same operation again. I switch and I switch again. That means the inverse of E3 is E3 itself. So you get 0, 0, 1, 1, 0. No, sorry. You can already see the bind. We've seen that if you multiply lower triangular matrices, you always get a lower triangular matrix. This is lower triangular. This is lower triangular. This is not. Well, you might still be able to get a lower triangular matrix. Let's multiply it out and tell me what is the product of these three. So I know the result of Gaussian elimination is this. What is this matrix? Again, don't do the individual elements. Try and do either row-wise or column-wise operation. I'm going to, let's say we multiply these two first. What do we get here? Yeah. First row is 1, 0, 0. Okay. Okay. Second row. 2, 1, 0. 3, 0, 1. The last row is kept as it is. Okay. What about here? Okay. One here, is it? Sure. 2, 0, 1. Okay. Well, 3 times the first row and 1 times the second row. Here. Sure. There are two ways to look at this, right? You can either say, I'm going to do row operations here using this matrix. Or if you look at this, this matrix is actually simpler because it only has zeros and ones. But this has zeros, ones, and other terms. So maybe if I use this as the matrix that gives me linear combinations, then it might be better. But the thing is, if I use this, then I have to work on the columns of this matrix. But let's try that. Here, the first column would be just the first column of this matrix. 1, 2, 3. The second column is essentially the third column. So 0, 0, 1. The third column is essentially the second column. That's all. You can verify it using the row operations as well. That means we get 1, 0, 0, 2, 0, 1, 3, 1, 0. That's not lower triangular. Okay, that means this does not hold. Okay, it turns out it does not hold whenever you do row exchange operations. Whenever you do row exchange operations, you essentially have to, you cannot do LU, but what you can do is this. If you essentially keep track of all the row exchanges that you did in the order in which you did them, and you multiply all of those into this matrix called P matrix, which we call the permutation matrix. Permutation is you're switching two elements, essentially the row exchange operations, right? If you can separate the row exchange operations out and do those row exchanges beforehand on your matrix A, okay, then that permuted A matrix, where the rows are arranged in the appropriate order, will have a LU decomposition. The original matrix does not, but once you correct for the order of the rows, then you still have LU decomposition. Let's do this. Let's try and see if that's what is. Let's try and find out for our example what is P. There is only one row exchange operation we did, right? Okay. What is the row exchange operation that we did? That actually turned out with this matrix for us eventually. Right? That's the only row exchange operation we did. Okay. Now let's do the same thing. Instead of doing the LU decomposition on A, let's do it on PA. Here P is simply P3 because that's the only row exchange operation we did. What will be PA now? So this will be 1, 0, 0, 0, 0, 1, 0, 1, 0 multiplied by what was my original matrix? 1, 1, 0, 2, 2, 1, 3, 4, 1. What will be my new matrix? Again, don't do it by hand. Look at it and see if you can tell me. If you look at this matrix, right? That's simply a permutation matrix. It's got only zeros and ones. That means you should be able to immediately tell me what the product is. What is the first row? second row. Okay, now do the LU decomposition for this, and then tell me if we do have an LU decomposition for PA, not A. We did not have it for A. Do the same thing, same LU decomposition, and see if you can have a LU decomposition for this matrix. So you'll essentially have to tell me what is E1 first, once you have it. Yep. 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 Ah, yeah, correct. Yes. And then, hey, hold on. Just check. Do you still have to do anything else? Once you do these two operations, what is the matrix you get? Okay. So what do you get after you do these two operations? What is the matrix you get? 1, 1, 0. 1. 1, no, because that's 0. That's it, we're done. You already got an upper triangular matrix. There are no other operations. The elements below the second pivot are 0. Now, this is then PA, because we started with PA, not A. Now tell me what will be if, well, both are lower triangular, their inverses will be lower triangular. The product has to be lower triangular. That means I should be able to get what is this? So this will be 1, 1, 0, 0, 1, 1, 0, 0, 1. So you have to find out D1 inverse, E2 inverse, and then multiply them together. We already know that. We've already done that here. E1 inverse, E2 inverse, that gives us this. No, sorry. I'm sorry. That's not correct. You'll have to redo it. They are not the same. These E1 and E2 are different from the previous E1 and E2. My apologies. Tell me what is E1 inverse. Yep. And then this gets multiplied by E2. This is E1 inverse. Yeah. Now tell me what is the product. You can use whichever view you want, the row view or column view. First row, you're telling me the first row or the first column? Okay. What can you tell me about the third row? The reason I'm asking the third row is because it only has zeros and ones. That means that should be easy to. Yes, that will simply be the third row. Now, what is the second one? Okay, it's 3 times this row plus 1 times this row. 3 times this is 3, 0, 0, 0, 1, 0. So that means if you add these two, 3, 1, 0. Lower triangular. So you have 3, 1, 0. Okay. Looks like what I've written down here is different, but I could be wrong. Just verify this. Or maybe did I start? No, okay. Just verify this. I think this is wrong. What we've done in class is correct, but you can verify this later. Okay, but that's the idea, and that's all I wanted to say. Okay, sometimes you might see people write it like this: A equals LU. We know the diagonal elements of L are all 1. The diagonal elements of U are not. In fact, they're all non-zero. They're guaranteed to be non-zero because those are the pivots. And our matrix is full rank. That means for a full rank matrix, you should have all non-zero pivots. Okay. Sometimes you might see people write it like this: L, D, U. Okay, where this is lower triangular, upper triangular. The only difference is U also has ones along its diagonal, and whatever were the pivot values, they're all in this D matrix, which is essentially a diagonal matrix. For example, let's say we'll take one example from before here. LU. Sometimes you might see people like you might see an expression like this. You take the upper triangular matrix, keep everything the same, except you make the diagonals 1. Okay, so here 1, minus 1, 2, 0, 1. Well, you don't simply remove them. So this will be 1, minus 1. You scale each row so that the diagonal is 1. And the diagonals, you didn't do anything to row 1. So that will be 1, 0, 0. You multiplied the second row by half. So this will be 0. Third row you multiplied by minus 1. So this is your L, D, U. So you might see things like this sometimes in LU decomposition. And another interesting property is if you have a matrix A, which is square and full rank, then you'll essentially have or okay, both your L and U will be transposes of each other. And that is easy to show. If A equals A transpose, and if A equals LU, A transpose will be LU transpose. What is the transpose of the product of two matrices? L. This is equal to LU. Okay? That means L must be U transpose. Sorry. And U must be L transpose. Okay. All right. That's all we have for this module. And we'll have in our midterm on Thursday, we will have everything including this lecture. Okay. Are there any questions so far? For everything that we've covered till now, this will be there for the midterm. No? Okay. Maybe then we'll do a couple of tutorials. Let's do this problem. Problem number 6. If you have AX equals this, okay, what we want to do is find the complete set of solutions to this problem. Well, we have to first find out if it's solvable. If it's solvable, then we need to find the complete set of solutions, even if there are infinitely many. Okay? So you essentially have to get A to the reduced row echelon form the augmented matrix, get it to the reduced row echelon form, and then from that see if it's solvable, and if it's solvable, what's the solution. What is the augmented matrix in this case for the sixth problem? Well, augmented matrix is simply A with the column B concatenated at the end, right? Augmented B. What is that? It will be 1, 1, 2, 4, 2, 2, minus 1, 3, 3, 3, 1, 7. Okay, what is the first thing we do? Well, Gaussian elimination steps. We have a non-zero pivot, so we try and make everything below that 0. So if we do that, what do you get? So you first row remains the same. This will be 0. Minus 5 is it? Okay. Huh? 5 or minus 5? Yeah. Okay. We can do this elimination in the bottom also, right? So what should we do to the third row now? I think you don't like the minus sign. It's minus 5. You're very positive, is it? Okay. All right. Okay. Now what do we do? So 1 was a pivot. So we go to the next diagonal element, that's 0. What do we do when we do reduced row echelon form? What do we do next? Original Gaussian elimination will say, well, nothing can be done, and you stop. Or you see if you can exchange rows, you can't here because everything below that is 0. You say, well, cannot be done, and stop with Gaussian elimination. But here you can't do that. Here you simply what you do, you move to the right, and you have a non-zero element, so that will become our new pivot. And below that is so now we proceed. We try and make everything below that 0. So you have 1, 2, sorry. 1, 1, 2, 4, 0, 0, 5, minus 5, 0, 0. Done. We can't do anything now. No more pivots left. Okay. Now, what is the rank of this matrix? Well, this is just the row echelon form. Maybe let's 2. Why is it 2? There are only 2 basic columns. What are the 2 basic columns here? Column 1 and yeah. Okay, so the rank is 2. Okay. Now, this is just the row echelon form. Let's do the reduced row echelon form. What do you do for that? Well, in the reduced row echelon form, what do we try and do? We make the basic columns unit vectors. That means we scale. So we try and make all the elements above the pivot position in the basic column 0, and we make the pivot positions, scale them to be 1. Okay. So let's say we choose the second row, and we want to make this pivot 1. So this remains the same. The top row remains the same, and we simply multiply this by minus 1 by 5. Right? If you do that, you get 0, 0, 1. Now we try and eliminate everything above this pivot 0. The last row remains the same. The second row remains the same. This will be what? 1, 1. Because these are 0, so whatever you add, scale and add, nothing will happen. Okay. Yeah. Those are our two basic columns. This is our reduced row echelon form. Now what can we say? Does it have a unique, is it solvable? No, first of all, is it solvable? Well, we could have said that directly from here, but we could have. What is the condition for the solvability of Ax equals b when you have? Sorry. Yeah. What should be lesser than the rank? It's probably there in the one sheet. Is it there? Oh no, I don't have Gaussian elimination on that. Well, the rank of A should be equal to the rank of AB. So whenever you have a 0 row, for the A part, the corresponding B part should be 0. If that was non-zero, then it's not solvable. Here that is satisfied. The last row of A is 0, the A component is 0, and the B component is also 0. That means the system of equations are consistent. If they're consistent, they are solvable. Okay, they are solvable. Is the solution unique? Why is it not unique? What is the condition for a unique solution in the reduced row echelon when you have the reduced row echelon form? Yes, here the number of columns should be equal to the number of basic columns. The number of columns is more than the number of basic columns. That means it has infinitely many solutions. Okay. If that is the case, how do we find out those infinitely many solutions? What do we do from here? Well, we simply take this and this. We'll call it A cap. We'll call it B cap. And we'll write down the expression A cap X equals B cap. Okay. So that'll be 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 2, 3. That will be equal to 2, 1, 0. That means our equations, which were originally x1 plus x2 plus 2x3 will be equal to 4. 2x1 plus 2x2 minus x3 equals 3. 3x1 plus 3x2 plus x3 equals 7 now reduces to x1 plus x2 is 2. x2 equals 1, 0. Okay. And when you have this, the next step we do is we express the components corresponding to the basic columns in terms of the non-basic columns. Okay. The components corresponding to the basic columns are x1 and x3. Right? Okay. So we keep that on the left-hand side. So we have x1 equals 2 minus x2, 1. Sorry, x2, no? Oh, sorry. Yes, yes. I'm sorry. Yes, I'm wrong. You're right. So yeah, stupid. Yes. Right. So we have x2 equal to x2. Okay. Now we can write this as your x vector is 2 minus x2, x2, 1, which is nothing but 2, 0, 1. That's the particular solution, plus x2 times minus 1, 1. Okay? That's the complete solution. Okay? Now, if you replace x2 by alpha, right? If you substitute this in the original equation, right? The left-hand side and the right-hand side should match. Let's just verify that. Okay. So my original matrix was okay, my x is this 2 minus alpha, alpha 1. What will that be equal to? That will be 2 minus alpha plus alpha plus 2. This will be 4 minus 2 alpha, 2 alpha minus 1. Be 6 minus 3 alpha, 3 alpha out. So I will get 4, 3. That's the complete solution. You can choose any value for alpha and that will be a solution for this problem. Okay. All right. Now, tell me if this is solvable. If it's solvable, find all the solutions. You can do the same thing. I won't do it. You can do it and tell me. Is it solvable? What is the last row that you get? When you do the reduced row echelon, you don't have to go to the reduced row echelon form. What is the last row? 0. Last element is minus 5, is it? So you get 0, 0, 0, minus 5. Is that correct? Okay. Okay. Tell me the row echelon form. So you would have started with 1, 1, 2, 1, 2, 2, minus 1, 1, 3, 3, 1, 1. When you get it to the row echelon form, what do you get? 1, 1, 2, 1. Is that correct? Okay, all right. So that means we started with this as the pivot. Now there is a pivot here, and the element below that is not 0. That means we have to now make that 0. So we can't stop. Earlier we stopped because all of them were 0 below the second row. We can't stop here. We continue. So 1, 1, 2, 1, 0, 0, minus 5, minus 1. Now is it solvable? I mean, always think of it like this. The last row tells me 0 times x1 there is no value of x1 and x2, x3 that will satisfy this equation. That means this is not solvable. That means this system of equation is not consistent. If this was 0, right, then yes, then we don't know. You can solve this equation. You can put any value of x1, x2, x3, and it's solvable. So this we don't have an inconsistent set of equations. See, I would go through this problem. Don't worry about the other ones. I would, for this, I won't worry about the basis, but for each of these, right, I would try and figure out what is the rank of the matrix using Gaussian elimination and all that, reduced row echelon form and all that. So I would practice that. That's something important. And then I would go through these as well. Okay. So here, if you have a matrix like this, and I ask you what is the A3, what does that correspond to? For a matrix A, what is this vector A3? No. What in words? Explain what A3 corresponds to. It's the third column, right? What about this? Yes, for transpose of the first column. What is this? What is the tilde do? What did we reserve the tilde for? No, we reserve the tilde for rows. That means this is, and we said vectors are always column vectors for us. That means we'll represent rows by a transpose. So what does this correspond to? Second row. No. Just the second row of A. The transpose already tells you it's a row. Okay. Can you tell me what this is? Can you compute this and tell me? So it looks like I'm multiplying a row by a column. That means I'm doing an inner product. Can you tell me the row and column here? So A1 till, sorry. A2 tilde. Minus 2. Minus 2 and yes. This problem is essentially to get you comfortable with the tilde, strange tilde transpose notation. Okay. And I would go through these as well. Okay, all right. Right, that's all. Then we'll meet on. So there is no class tomorrow because I'm not here, but we'll shift it to Friday. All right. Thank you.